Hi, my name is Ted Letcher, and I'm a PhD candidate at the University of Albany. My research specialties focus on snow, regional climate feedbacks, and mountain meteorology. As part of that research, I'm researching the influence of the snow albedo feedback on the regional climate response to large-scale global warming over the Rocky Mountains of Colorado. So the Rocky Mountains of Colorado are a very important source of water for much of the western United States, and a lot of efforts and research has gone into developing, evaluating, and using regional climate models to determine and try to project how water resources are going to be affected in the future. The snow albedo feedback is a positive climate feedback that amplifies warming where snow cover is lost by decreasing the albedo of the surface and allowing more absorption of solar radiation. This feedback is particularly active in mid-latitude mountain regions such as the Rockies, where snow cover persists well into the spring months when the solar insolation is high. To lay out how the snow albedo feedback can influence precipitation on the Great Plains, let's head on over to the whiteboard. So to flesh out exactly how the snow albedo feedback taking place within the interior Rockies can influence the convective environment and precipitation downstream, we've drawn this idealized cross-section showing the Great Plains here to the east, leading back up to the Front Range, and then the interior Rockies to the west. So what happens in a typical day is the boundary layer develops, and because you have two very different climates here, you have a boundary layer that develops here, dry neutral, with a capping inversion aloft, maybe not quite that strong. And here in the Rocky Mountains, you have basically the same thing going on. The boundary layer development's a little bit stunted by the presence of snow cover, so it might look something not quite as dry neutral, not quite as deep, but again, the same basic principle exists here. So what we're interested in is how the development of this boundary layer here changes due to the snow albedo feedback. So now that we've warmed the climate, the snow line has retreated from where it was, further up in elevation, and now the interior Rocky Mountains are no longer snow covered. Through the snow albedo feedback, this increases the amount of warming here at the surface, which leads to a deeper, more vigorous boundary layer. Now how does that affect the downstream environment? Well, if you remember here, our elevated residual layer left over from the snow-covered Rockies. Now, what we've essentially done is we've changed the characteristics of this layer. So if we look at it now, we have a warmer temperature here. So I'll draw that line. And then we've also increased the lapse rates and deepened the layer. So this changes the convective environment here in two ways. It increases the lid strength, or the capping inversion, which inhibits convection earlier in the day, but it's also increased the mid-level instability, or the overall amount of CAPE available for convection to realize. To illustrate this, here are a pair of soundings that show a weak elevated mixed layer and a strong elevated mixed layer to indicate how the snow albedo feedback may influence the temperature profile downstream over the Great Plains. To tackle this research question, I propose working with a hierarchy of regional climate models centered on the Rocky Mountains and the Great Plains. This hierarchy will range from advanced, high-resolution, multi-year regional climate experiments complete with full atmospheric physics and coupling with realistic land surface models, all the way down to super high-resolution case study experiments. In performing all of these simulations, we will better understand how regional climate sensitivity varies according to, for example, choice of land surface model. The focus of this research on the Rocky Mountains and the Great Plains allows for the potential collaboration with the North American Water Program, RHP. This proposal falls within the scope of several of the GEWEX science imperatives. For example, this project fits very well with both the data sets and the modeling categories. By running multi-year high-resolution climate simulations, new model data sets are generated and opportunities for model evaluation against satellite and in-situ ground observational data sets are opened up. For example, these simulations can be compared to high-resolution satellite data sets to evaluate snow cover parameterizations for various land surface models. Because of the role that the snow albedo feedback plays in this region's climate, and the fact that most of the runoff in the Rockies derives from snow cover, this is an important variable to model correctly. Thus, developing new opportunities to improve snow cover in regional models is critical to the GEWEX objectives. Additionally, by using regional climate models run at convection-resolving scales, the uncertainty in cloud and precipitation feedbacks, as well as weather extremes that arises due to limitations in course resolution can be better understood. Through this approach, regional trends and extreme weather events can be attributed to specific climate processes. Additionally, by quantifying regional climate feedbacks as well as land-atmosphere energy budgets and how sensitive these quantities are to land surface models and model resolution, a better understanding of future uncertainty in regional climate projections is attained. This project also falls within the processes science imperative. Again, by running simulations at high enough resolution to explicitly resolve phenomena not typically resolved in climate models, various parameterizations can be evaluated and uncertainty in regional climate projections can be further reduced. Lastly, the Rocky Mountains and the Great Plains are two very different climate zones. However, this divide is not well represented in global climate models, as the Rockies are generally treated as a simple and broad plateau that rises gradually from the Great Plains, rather than an abrupt transition to a series of narrow mountain ridges and elevated valleys. By using models that can properly resolve this transition and investigating a connection between these climate regions, we can explore a previously unexplored regional scale interaction that occurs along discontinuities in climate zones. Furthermore, because this interaction is relevant for precipitation over major agricultural regions of the United States, there are potential significant societal impacts as well. There are a few difficulties in performing this research. First and foremost is the computer resource problem. A lot of computer resources need to be devoted in order to perform high-resolution regional climate simulations. In one regard, these simulations have to be performed over a long time period. Seasonal to decadal scales of regional climate simulations are required. And if we're looking at running simulations over a larger region of the western United States at convection resolving grid spacing for multi-year simulations, that takes up a lot of computer resources. The second issue we have is our focus on convection. Convection is a highly stochastic process that is influenced by a variety of different factors. And in order to draw a causal link between the snow albedo feedback and downstream convection, we need to perform highly controlled experiments, which means we need to control for factors such as planetary boundary layer schemes and land surface model choice and different microphysical schemes in order to ensure that we're able to draw a robust link between the snow albedo feedback and our downstream convective processes. So the third issue we're looking at is spin-up time and model sensitivity. We need to determine how sensitive these results are to minor tweaks in model configurations, such as horizontal resolution or spin-up time or sensitivity to land surface model as well. So these are just some of the difficulties that we're going to encounter in looking at these connections going forward as part of our research process. And all of this feeds back into our computer resource problem. If we have to perform several different simulations in order to solve the sensitivity problem, we've compounded the computer resource problem in doing so. So the main difficulties in this research are going to be trying to find a balance that is able to basically navigate and solve these problems simultaneously while still being able to develop robust scientific results. Lastly, because the Great Plains serve as a major agricultural center for the United States, both in terms of wheat, corn production, soybean production, and a whole bunch of other agricultural concerns as well, it's extremely important that we understand how the precipitation in this region may be influenced in a future climate. And better understanding the processes involved in changing downstream precipitation patterns will help us going forward into the future in terms of policy decisions and determining how exactly we can better prepare for the future climate and mitigate any issues that come up as a result.